Hi there, my name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. Previously, in this series on analog circuits for music synthesis, we looked at some fourth-order filters that commonly appear in synthesizers. And we looked at implementations using operational transconductance amplifiers and a particularly famous differential ladder implementation by Bob Moog. For the rest of the course, we'll be focusing on second-order filters, and just as we did with fourth-order filters, we'll first start by exploring some properties of the overall mathematical structure of such filters, and future lectures will address specific implementations. Here we see some transfer functions, aka system functions, for low-pass, bandpass, and high-pass second-order filters. Notice that all of these transfer functions have exactly the same denominator. The parameter omega n is called the natural frequency. Here it is in terms of radians per second. You could divide that by 2 pi to get an Fn, the natural frequency in hertz. And there's this parameter q, which is the quality factor. The only substantive difference between these transfer functions is that the bandpass version has an s in the numerator, the high-pass version has an s squared in the numerator, and the low-pass version doesn't have any s in the numerator. The omega n squared that you see here and the omega n over q are convenient normalization factors, and we'll see why I wrote those there in a second. Notice over here on the right, I'm drawing some partial pole zero plots, partial in the sense that I'm only showing the zeros. We have 1 0 for the bandpass at the origin, and we have 2 zeros at the origin for the high-pass filter. I'm not drawing in the poles yet because the whole rest of the lecture will basically hinge on figuring out where the poles are for different values of Q. Remember that zeros are the locations on the complex plane where the transfer function evaluates to 0, and we're putting the real part of S along the horizontal axis and the imaginary part of S along the vertical axis. So first, let's make sure the names low-pass, bandpass, and high-pass are earned by plugging in j omega for S to derive frequency responses and see what we get when we plug in 0 for omega and for when we let omega go to infinity. So plugging in j omega for S here, and plugging it in here, and then plugging in 0 for omega will give us the gain at DC. So this term here goes away, and this term here goes away, and we're left with omega n squared over omega n squared, which gives us a 1. And now you see why it was convenient to put this omega n squared in the numerator. If we didn't have the omega n squared here, we would have a 1 in the numerator here, and the gain at DC would be 1 over omega n squared. But putting it there provides a convenient normalization that gives us a value of 1 at DC. Okay, so now let's ask the question, what happens if we let omega go to infinity? Well, roughly speaking, I have a bunch of terms in here with omegas in them, and as omega becomes bigger and bigger, all of that's eventually going to swap this constant. And a constant like omega n squared over something going to infinity, I'm being a little loose with my thinking here, which is why I'm putting the infinity in quotes, is going to give you 0. So this is a beautiful thing. We have a magnitude of 1 at DC, and then it's going to slope off to 0. Now, what I've told you is only a partial truth. This only happens for certain values of Q. There are other values of Q that will give you a little bump in the frequency response where it will actually go up before the cutoff and it slopes off, and we'll look at that later. What about the bandpass filter? Well, we'll now have a j omega that's introduced in the numerator along with this new omega n over q normalization factor instead of the omega n squared for the low pass. Now, if we plug in 0 for omega again, we wind up with 0 in the numerator, some zeros in the denominator, and we wind up with 0 over some constant. And what that constant is doesn't matter much because that gives us 0. So we have 0 at DC. In the limit, as we let omega go to infinity, as omega becomes bigger and bigger, the omega squared in this first term will eventually swamp the effect of this omega in the second term. So we could imagine asking what happens as omega goes to infinity if we have just this j omega squared in the denominator. And if you look at that term, you realize, well, one of these j omegas is going to cancel in the numerator and the denominator. And so we're left with a constant over something going off to infinity, and that's going to give us 0. So the bandpass filter is 0 at DC, slopes up, comes back down somehow. This is not a work of art. Hopefully you get the general idea. It does eventually go to 0 at high frequencies too. So it's only passing frequencies within a certain band. And although I won't prove it here, it's not hard to show that the peak of the magnitude response of the bandpass filter is indeed at omega n, the natural frequency. Okay, you know the drill by now. We plug in 0 for omega and see what pops out. We find we get 0 over omega n squared, which gives us 0. So the high-pass filter at DC gives us 0, which makes sense. What about the case as we let omega go to infinity? We can argue that the omega squared kind of term in the denominator starts to swamp the omega term and the constant term. So as omega is approaching infinity, the denominator looks more and more just like j omega squared, and we have a j omega squared in the numerator, so that gives us 1. So our high-pass filter nicely starts at 0, rises, and then asymptotes at 1. And again, this is not a work of art. And again, it's also only a half-truth. This monotonic increase only happens for certain values of Q, and there are values of Q where if you're coming in from the right, you'll get a peak around the cutoff before you hit the drop. And we'll see how that works later. So now let's consider the poles. The poles of a transfer function are the places on the S-plane where the transfer function blows up, and in this case, the transfer function blows up in the places where the denominator of the transfer function goes to 0. So if we set the denominator equal to 0, we can use our good old-fashioned quadratic formula, which will give us two possible solutions. And after applying the quadratic formula, we see there's an omega n squared here and an omega n squared here, so we can factor that out. And when we factor that out of the square root, we wind up with an omega n in front of everything. The really interesting question here about these two poles is, when are the poles complex valued? Because if they're complex valued, that means we get wiggles in the time domain. We'll see some oscillations on the oscilloscope. So they'll be complex valued when the stuff under the square root goes negative. So if we ask, where does the stuff under the square root go negative? This incidentally is referred to as the underdamped case. Let's just move over the 4 here. And then we can flip both sides of the equation upside down, but when we do that, we have to remember to flip the sign on the inequality. And taking a square root, we see that for Q bigger than a half, we have this underdamped case. And that's the case where we will see oscillations on the oscilloscope. So that represents oscillations in the time domain. So the fact that I have bigger than 1/2 here suggests that something interesting may be happening at 1/2. Well, that's referred to as the critically damped case. So if we plug in 1/2 for Q, we wind up with a 2 here in the denominator, and that readily factors, and we see that we have two poles sitting on top of each other at minus omega n. So this is basically the case where you have two identical filters, each of them is a single pole filter, and both of them have a half-power cutoff point of omega n. What about the case where Q is less than 1/2? Well, in that case, the poles are both real valued. As a particular example, let's try Q equals 1/4. We can plug that in, just do the computation, and what you'll see in this example, and is also true in the general case, that you'll have one pole on one side of minus omega n and another pole on the other side of minus omega n. And basically what happens is, as the quality factor increases, these poles start to move in towards each other, and they eventually hit that omega n point at Q equals 1/2, and then you're left with that critically damped case. Similarly, if we were to decrease the quality factor further, then the poles would be spreading apart again, and this pole will start to get closer and closer to the origin, and this pole will keep going out to the left and having a smaller and smaller effect on the filter's behavior. I probably should have mentioned earlier, we're always assuming that Q is bigger than 0. Mathematically, if Q is less than 0, that would give you a pole on the right-hand side of the plane, and then the system would be unstable, and we wouldn't be talking about frequency responses anyway. All right, so imagine we're starting with an overdamped case with low Q. We start increasing Q, and these poles start going towards this minus omega endpoint. They eventually hit the minus omega endpoint when we hit Q equal 1/2. That corresponds to the critically damped case. And at that point, if we keep increasing Q, then we wind up with a case where the poles split apart and then start traveling on a circular path with a radius of omega n around the origin. So the particular case of Q equal 1 over square root of 2, that's like 0.707, that's very special. That's this case where the poles form 45-degree angles with our axes. So in the underdamped case, if we imagine starting at Q equal 1/2, where we start with both poles here, and then we start to increase Q and we go into the underdamped case, moving away from the critically damped case, at first we're still pretty close to the horizontal axis here. We eventually hit that very special Q equal 1 over square root of 2 point. And then if you keep going, we start to approach this imaginary axis. At basically perfect quality, Q equals infinity, that middle term in the denominator goes away. And if you look at the inverse Laplace transform of that transfer function, that's a sinusoid. So at that particular point, the poles land at plus j omega n and minus j omega n. And at that point, the filter is now self-resonating and acting as an oscillator at a frequency of omega n. Of course, divide that by 2 pi to get the frequency in hertz. So far, I've sort of implicitly described everything in terms of low-pass filters, but everything I've said so far also applies to the bandpass case where you have single zeros at the origin and to the high-pass case where you have double zeros at the origin. Now, there is something interesting that is specific to just the high-pass and low-pass, and it has to do with these 45-degree angles. For Q bigger than 1 over square root of 2, you get a peak in the frequency response. It's not monotonic anymore, as I alluded to earlier. For the low-pass filter, the location of that resonant peak, the highest point of the magnitude of the frequency response, is the natural frequency multiplied by some factor that makes that frequency be lower, having to do with the quality factor Q. So the higher the quality factor, the smaller the term, meaning the bigger this term is, and the closer omega r is to omega n. For lower quality factors, this term would be bigger, meaning that this whole term here would be smaller, and the resonant peak is closer towards DC, further left on the plot. Now, for the high-pass filter, the situation is the opposite, and interestingly, the formula is quite similar. You see this factor here, except here it's in the denominator. So in this case, for low Q, this term is large, meaning that this term is small, and when you divide by a small number, you get something very big. So when you start seeing a resonance bump, it's way out at infinity. And as you increase the quality factor, this term gets smaller, and this term gets closer to 1. So as you're increasing the quality factor, the resonant bump is getting closer and closer to the natural frequency, but this time it's coming in from the right on the plot. Notice, though, that these resonance peaks only occur for Q bigger than 1 over square root of 2. And if you look at these formulas, you see that must be the case, because if you had Q less than 1 over square root of 2, you would wind up with a negative number under the square root, and that would give you an imaginary number here, and that wouldn't make any sense at all. I'm not going to prove these properties here. It would take a while to prove these properties, so I'm not going to do it here, but it's fairly straightforward. Basically, you write out the magnitude of the frequency response and take some derivatives. And in some cases, those derivatives become easier if you do some simple transformations first. So we've been describing everything in terms of this quality factor Q. There's an alternate parameterization involving something called the damping ratio zeta. That's just 1 over 2Q. And then you could also go the other direction and say Q is 1 over 2 zeta. People who work in filter design usually describe things in terms of Q, whether they're designing audio filters or RF filters. And people who work in feedback control theory tend to parameterize things in terms of the damping ratio zeta. Something special about this 1 over square root of 2 number is that if we plug in Q equals 1 over square root of 2 into this formula, we wind up seeing that the equivalent condition for resonance bumps in the high pass and low pass case is just that zeta is bigger than 1 over square root of 2. The 1 over square root of 2 stays fixed. Now, one convenient thing about the zeta notation is it does tend to make a lot of the expressions more compact. You can sort of write them on one line, and you don't need these divisions. So in the low pass case, we have omega n times square root of 1 minus 2 zeta squared. And for the high pass case, we have omega n over square root of 1 minus 2 zeta squared. So here's an example of magnitude frequency response plots for the low pass case for different values of zeta. And if I was doing these from scratch, I would probably plot these in terms of Q, but I'm being lazy and borrowing this graph from a textbook I'm writing for our ECE4450 Signals and Systems class. And in that class, we mostly use the zeta damping ratio notation. So the main interesting transition point is zeta equals 1 over square root of 2, which is equivalent to Q equals 1 over square root of 2. And that's this purple line right here. Incidentally, this is the response of what's called a second-order Butterworth filter. A Butterworth filter basically has the steepest response you can get and still maintain a monotonic frequency response without bumps in it. Now, for higher damping factors or equivalently lower Q, you get these much sadder-looking frequency responses. But for lower damping factors, in other words, higher Q, you see that resonance bumps start to appear. Now, all of these plots are for the same natural frequency of 10 Hertz. Of course, this is a good deal lower than the audio range. I'm not sure why I actually did that when I was originally making these plots. I wasn't really necessarily making these with audio in mind. But anyway, the thing to note is that it's not like the peaks are definitely always at 10 Hertz. At lower Q values, when the bump is starting to just barely appear, the bump isn't very high and it's kind of wide. But as you increase Q, you wind up getting peaks that are both taller and narrower. And as you're really increasing Q, that peak is getting pretty close to the natural frequency. Now, if you've seen these kind of plots before, you've probably seen them Bode style, which means both the horizontal and the vertical axis are plotted on logarithmic scales. But I think there's some advantage into peeking at these with scales in the linear form at least once or twice. Here's the same scenario except for the high-pass filter. Again, we have this purple line here, which is that magic Butterworth filter line. This is as steep of a slope as you're going to get without having bumps in the response. And as you increase Q, the bumps that start way out here at infinity and aren't very tall get taller and become more narrow. And when you really crank up Q, then the peak is really starting to approach that 10 Hertz mark, but this time it's approaching it from the right. So obviously the bandpass response is quite different than the low pass and high pass cases. Here, you always have a peak, and it's always at whatever the natural frequency is. The main thing that zeta, or equivalently Q, controls is the bandwidth of the filter. So for low damping factors or equivalently high Q, you get very narrow filters. For higher damping factors or equivalently lower Qs, you get wider bandwidths. Now, the plots I'm making here use that normalized transfer function that had the omega n divided by Q in the numerator. If you don't include that minus Q, you get this unnormalized response that is usually actually musically a bit more useful. So if you don't include that normalization factor, as the response is becoming more narrow, it's also becoming taller. And that's usually more musically useful because if you're just decreasing the bandwidth, you're just chopping out more of the sound. And regardless of what else you're doing with relative frequencies, the thing is just naturally going to sound softer. But here, if you have that normalization term in there, as things are becoming more narrow, they're also becoming taller. And roughly speaking, these effects tend to balance out. So you have this feel of a changing bandwidth, but without sensing a massive volume change. But your mileage may vary. Here I'm showing some examples for a damping factor of zeta equals 1. That's basically Q equal 1/2. And this is for a set of rising natural frequencies. So in the previous plots, I've kept Fn fixed, but I've changed Q or equivalently zeta. Here I'm keeping zeta, aka Q, fixed, but I'm changing Fn. Now, this case corresponds to just two standard one-pole low-pass filters with a cutoff frequency in series with no fancier tricks. So the half-power point of one of those filters is like 0.707, 1 over square root of 2. So when we run it through two of those, we get two of those, and we wind up with a magnitude of 0.5 at our cutoff. And you'll see that consistently all the way through the examples given here of 10, 20, 30, 40 hertz. Be careful, this isn't a power plot. The power here would actually be cut down by a factor of 4 at that cutoff frequency because you've got two of those filters cascaded. Now here's that Butterworth filter example for zeta equals 1 over square root of 2, or equivalently Q equal 1 over square root of 2. This is as steep as you're going to get with a second order filter without having bumps in the frequency response. Notice that at the particular key frequencies 10, 20, 30, 40 that I'm plotting here, in this case, the magnitude is around that 1 over square root of 2 point. So if you ask what's the power would then be 1/2 at the cutoff. All right, so let's lower the damping, aka increase Q. Now we see that there are peaks in the frequency response. And one interesting thing about the way this behaves is that notice that as we're increasing the frequency, at least looking at things on a linear plot, it looks like the bandwidth is also increasing from the relatively narrow-looking bandwidth over here. That's actually musically useful because humans perceive pitch on a logarithmic scale. So if you were to sweep this natural frequency and somehow this bandwidth here was staying the same, then as you would increase the frequency, it would sound to the listener like that's taking up less and less pitch space. But just the way that equation works out, as you're increasing this Fn, essentially the width of the peaks here are also increasing to sort of correspond with how humans hear. So you can sweep Fn up and down, and the human listener will perceive the same bandwidth in pitch space, even though it's changing in this linear frequency space, which I think is pretty cool. So something that's really interesting about the bandpass response, and here I'm using the normalized version, is that if you take any horizontal cut, and you see where that cut crosses one of these magnitude frequency responses and draw lines down. Let's call the place where the cut crosses the magnitude response line on the left F sub L, and let's call the place where it intersects on the right F sub U. So these correspond to our lower and upper frequencies. And let's call Fn, the place where the curve has its peak, Fc for the center frequency. Now, notice viewing this on a linear scale, we have a lot more frequency change on the right than we do on the left. And it kind of makes sense that that has to happen. If you think about changing Fn around, no matter where you put this, it always has to come back to 0 on the left, but it somehow has to go to 0, stretching out over an effectively infinite amount of space on the right. So it makes sense that it's more smushed over here than over here. But here's an interesting fun fact. The center frequency is equal to the square root of the lower and upper frequencies multiplied together. And that should make you think about logarithms. If I take the logarithm of both sides, we see that the logarithm of the center frequency is indeed the arithmetic average of the logarithm of the lower frequency and the logarithm of the upper frequency. So although the center frequency isn't the arithmetic average of F sub L and F sub U, it is the geometric average. And this fact is one of the things that kind of justifies plotting everything on a Bode scale, because then when you plot this on a Bode scale, it will look symmetric around that center. And that both looks nice in terms of making a plot and matches the way humans perceive pitch. And what's interesting is this property works no matter what horizontal cut I take. If I take the same plot, but draw that cut down here somewhere, well, I can draw a new F sub L and a new F sub U, and this property still holds. And this is really musically cool. Imagine that the math somehow gave us filters where things were kind of more or less even on either side. The effect of our bandpass filter would sound a little lopsided to our ears. If we really had a frequency response that was somehow more symmetric, say like this, where the blue line on the right really looked more like a mirror image on this linear scale of the blue line on the left, we would probably perceive this as being bass heavy, because our brain would be perceiving those frequencies on the right as corresponding to smaller chunks of pitch space. So let's dig a bit deeper into the definition of Q. Here, I'm not just drawing any old horizontal cut. I'm drawing the cut at square root of 2.707. So that's the half power cutoff point. Now, let me define a bandwidth as being the f sub u minus f sub l, but not just any old upper frequency and lower frequency, particularly for this half power point. Then it turns out that Q is equal to this max frequency divided by the bandwidth. Or equivalently, the bandwidth is the max frequency divided by a Q. This is interesting because it means that Q is a much more musically convenient parameter than the raw linear bandwidth. If I were to change the center frequency but keep the bandwidth fixed, again, a human will perceive the frequency response of using different amounts of pitch space. But now imagine that I fix Q and then I change this center frequency. Well, to keep Q fixed, if I increase that center frequency, the bandwidth also has to increase along with it. So it will naturally expand to handle how humans will perceive that linear bandwidth in terms of wanting to hear bigger in bandwidths at higher frequencies to constitute the same overall amount of perceived pitch space. And it's amazing that this Q then is so tightly integrated into the equations that define the second order response. So you can go down to Guitar Center or Samash Music, and you will find synthesizers with a knob on them labeled Q, or resonance, or emphasis. And if it's a second order filter, that's this Q. That's the Q in those equations that's being specified by that knob on that synthesizer. Now, I want to give you a word of caution. Although Q here is playing a role similar to the feedback factor K that we saw in the 4-pole with feedback structure, it's not the same. It plays a similar role, but it is a different, distinct thing. K can vary between 0 and 4, including 0, but not really including 4. Q can vary between 0 and infinity, but technically speaking, not include 0 or infinity. So returning to the issue of the low-pass and high-pass responses for a second, I would like to leave you with a thought about the damped oscillation frequency, and this is the frequency of the wiggles that you see on the oscilloscope. The important thing to note is that the frequency you see on the oscilloscope is not the same as the peak frequency of the frequency response. They are different things. I'm doing everything in terms of zeta here just because it makes the equations a little more compact, but the expressions for where the resonant peak is have a 2 in front of the instance of the zeta squared, whereas the expression for what the damped frequency is, namely what oscillations you see appearing on the oscilloscope if you, say, put in impulses or maybe a square wave, well, that doesn't have the 2 sitting in front of there. And that makes sense because our conditions for seeing oscillations on the oscilloscope are different than for having a bump in the frequency response. To have a bump in the frequency response, the magic Q and or zeta is 1 over square root of 2. But remember that to have complex poles, which give us a sinusoidal response in the time domain, we need to have either Q bigger than 1 over 2 or equivalently zeta less than 1. So the critical damping case between underdamped and overdamped is zeta equals 1 in terms of the damping ratio. And then this equation makes a bit more sense because the stuff under the square root here is only positive if zeta is less than 1. Now, interestingly, this damped frequency formula applies to both the low-pass and high-pass cases. And I confess, I didn't really understand the fact that these were different until around the second time I taught ECE4084, our Signals and Systems class. I always assumed that these were equivalent. If I saw ringing on the oscilloscope, I assumed that then that was probably the frequency at which you would get a peak in the frequency response. But they are slightly different. Now, the reason that I think it's reasonable for somebody, not just me, to assume that might be the case is that for low zeta, omega R and omega D are pretty close to each other. And I think by the point that you notice that resonance bump, these formulas would be giving you pretty similar answers, basically because both of these formulas for very low zeta quickly approach omega N. So going back to this chart, Remember that for the critically damped case, we had both of our poles sitting at minus omega n. And that's basically two low-pass filters. Each of them has just one pole and a cutoff frequency of omega n, and it's one after the other. We also had the overdamped case, where we definitely don't have any peaking in the frequency response, but we also don't have oscillations in the time domain. And this particular case is particularly uninteresting also because you could achieve it by just having two one-pole filters, one after another with different cutoff frequencies. It's not that interesting. In order to get this kind of effect, you need something that's specifically creating a second-order structure. Just a couple of one-pole filters cascaded without any feedback or other weirdness going on won't do it. But once we're in that underdamped region, we see that there's two interesting cases that are delineated by this Butterworth filter line, this 45-degree angle. For Q that's bigger than a half, but less than 1 over square root of 2, or equivalently zeta that's less than 1, but above 1 over square root of 2, you get ripples in the time domain, but you don't see a peak in the frequency response. Once we cross that Butterworth line, we're now into this region here, where Q is bigger than 1 over square root of 2, or equivalently zeta is less than 1 over square root of 2. And here you see ripples in the time domain, but you also see a peak in the frequency response. And if we keep pushing that far enough, and we removed all the damping from the system, we essentially have an infinite Q factor, effectively speaking. Then you're sitting on the imaginary axis, you don't really have a well-defined frequency response anymore, and the filter will self-oscillate.